I'd just like to start by declaring my conflicts. I have research support and consulting activities with Siemens. And what I'd like to do for the next few minutes is describe the optimization of pulse sequences for molecular imaging of hyperpolarized agents with a particular focus on carbon-13 compounds. Now, as we saw in the last talk, one of the hallmarks of a hyperpolarized agent is that we have this large non-equilibrium longitudinal magnetization. And remember that non-equilibrium refers to where we're going to image it, that is, at body temperature and at field strengths of a few Tesla. So the relaxation of this magnetization is, of course, governed by the standard equation, as we have here. We have a recovery to thermal equilibrium term and a decay of the initial magnetization term. But the important point for hyperpolarized compounds is that the initial magnetization is so much larger than thermal equilibrium that this first term is negligible. What this means is that T1 relaxation only depletes the magnetization that we have. And since there's no recovery after the RF pulses we apply also deplete the magnetization. So that's very important to consider when we're designing the pulse sequences. If we consider these properties together with the fact that for most of the agents we use, the T1 values on the order of tens of seconds, and we can have magnetization that's exchanging among molecules in the case of carbon-13 or in other hyperpolarized applications like xenon-129 among binding states that have much different chemical shifts. Considering all these properties together leads to a couple general design themes for hyperpolarized acquisitions. First of all, we need to very carefully manage this non-equilibrium magnetization that we have. This leads to optimization of the RF excitation history and tailoring the RF excitation for exchange of the magnetization among compounds with different chemical shifts. Also, considering the T1 lifetimes of the compounds and the limited amounts that we typically have, it's often, particularly with dynamic acquisitions, very important to accelerate the spatial and spectral encoding. So we're going to talk about these two main topics for the rest of the talk. Now, one of the simplest things to do as far as managing non-equilibrium magnetization is just to use constant low flip angles. And for many applications, this is perfectly adequate. This timing diagram down at the bottom shows an interesting way to do this. This is a low flip angle double spin echo pulse sequence. We see a low flip angle alpha pulse followed by two adiabatic refocusing pulses. And the combination of these three pulses close together has essentially the same effect on the magnetization as just the low flip angle alpha pulse, but it lets us have the advantage of the spin echo framework for the pulse sequence. Now, we can get a little bit more advanced from just using the constant low flip angle and turn to variable flip angles during the acquisition, which lets us modulate the consumption of the magnetization. The most common way that this is applied is that you derive a set of flip angles that come from the equation shown here that give you constant signal in the absence of T1 relaxation. This was in fact envisioned quite a few years ago by Peter Mansfield and has been used in lots of hyperpolarized applications. Here's an example of the pulse history that we might get for, I think this is about 30 pulses. And one thing to note is that the last pulse is 90 degrees. So at the end of the acquisition, you use up all the remaining magnetization, but maintain a constant signal. Now, it's important to note that this type of flip angle variation does have some limitations. First of all, it's sensitive to incorrect flip angles. This could happen, for example, due to B1 inhomogeneity or due to inaccurate transmitter calibration. But the point, as shown here on the left, is that even if you're trying to achieve a constant signal, if you have significant variation in the flip angles, you might get either a signal that dives a lot at the end of the acquisition or increases quite a lot. But this is very easy to deal with. What you can do is instead of deriving flip angles that give you the maximum signal, if you simply reduce this a little bit, here we've shown targeting the signal just 5% less, then even in the face of B1 inhomogeneity or incorrect flip angles, you get more or less what you ask for, more or less what you wanted. Another problem, if you're doing slice selection with variable flip angles, is that you can get substantial distortion of the slice profile as you proceed to the higher flip angles. Here on the left, we show how the slice profile evolves from the beginning of the acquisition to the end, and we see at the end with 90 degrees, we have no signal in the middle, but we have these large sort of wings or ears on the slice profile. Again, we can deal with this by just targeting a signal level that's a little bit less than the maximum, and you get a much better behaved slice profile. Now, when we do things with carbon-13, such as metabolic imaging, you know we're not going to just have one resonance, but a number of dependent resonances. For example, pyruvate that's metabolized into lactate and other metabolites. And in this case, the considerations for designing the flip angles get a little bit more complicated. And it leads us, for example, let's look at this simple case where we just have two things, pyruvate being metabolized to lactate. And if we consider just using constant 20-degree flip angles, we might get something like this. We note that we've plotted pyruvate divided by 10, so actually the pyruvate signal is much higher than the lactate, and then the lactate comes up and then goes back down due to the RF pulses and T1 relaxation. However, if we realize that the pyruvate is our magnetization source, then maybe we could do something a little bit smarter, like use a lower flip angle on pyruvate compared to lactate. Here we've used only 1 degree on pyruvate. We still get a nice signal from it, but we get about a 50% increase in lactate by shifting the higher flip angle to the downstream metabolite. So this leads to a general principle that when you have this type of situation, it can be very advantageous to use metabolite or chemical shift-specific flip angles. And this is something that's been applied with great profit in the field. So this leads us to more advanced RF excitation approaches. Many of these have been based on so-called spatial-spectral excitation pulses. One approach that's been used is excitation of individual metabolites, and another one is to excite several metabolites at once, but to tailor the flip angles and optimize them to the individual compounds of interest. So we'll look at both of these. Just a brief bit of history, let's talk a little bit about spatial spectral excitation. This was developed a number of years ago by Craig Meyer, and the original application was for fat water imaging. Now what we see is instead of the standard selective excitation where we just have a constant gradient in RF pulse, what we have is a time varying gradient in a tailored RF waveform that's played out during that time varying gradient. What that lets us do is localize in both space and frequency. So we can place things we're interested in at the high excitation spots like water and things we're not interested in like fat where we don't have much excitation. Now here's that applied in the context of carbon-13. This is some work from Angus Lau. Here's a spatial-spectral excitation pulse. We see it looks a little bit more complicated than the one we saw on the previous page. And here is its excitation pattern shown in color. So blue is where we don't have much excitation, up to red is maximum excitation. So we have high excitation at these 2 points and a little bit less outside. Here in white is a representative carbon-13 spectrum. And so the idea is that we can take a metabolite of interest like bicarbonate, place it where we have high excitation, and the other metabolites fall in between the excitation lobes. So you get essentially no signal from them. Or we can move it around. Here we can excite lactate and not the others, or here pyruvate and very little excitation of the others. So we can select what we want. Here's an application of this idea where we place it on bicarbonate. We place it on, bicarbonate's here and we imaged. We see bicarbonate in the wall of the heart. Or we place it on pyruvate here and we see pyruvate in the heart cavity. Now, a little bit more complicated approach is to optimize the flip angles for several metabolites at once. This is some work from Peter Larson. Here we see the spatial spectral pulse, the RF waveform, and the oscillating gradient. This is more complicated than what we saw before. We see it has imaginary and real components. And what we've done is design it so that we get low excitation at pyruvate, which is that's our feeding magnetization pool. And we get much higher excitation at downstream metabolites, in this case alanine and lactate. Down on the lower right, we just see a grayscale representation of the spatial and spectral properties of this pulse. Now, we can combine this idea with the variable flip angle concept I introduced a few slides ago. So we can both have different flip angles for different metabolites, and we can vary them differently depending on what they are. So for both lactate and alanine, what Peter Larson did was vary them. This is the variable flip angle that gives you constant signal, ignoring relaxation, but a different variable flip angle variation for the pyruvate. And here's some experimental results on the right that show you what you can get from this type of approach. At the top, we have the dynamics for a 5-degree constant pulse. Here, sort of like the example I showed, we see very high signal from pyruvate. This is pyruvate divided by 4, and much lower signal from the downstream metabolites of interest. But if we go to this optimized spatial spectral pulse, then all of a sudden, things like lactate here in light blue and alanine in red have a much higher signal than the constant degree pulse and much more comparable to the pyruvate. An interesting application of these spatial spectral pulses is shown here, where we're quantitating the metabolic exchange rates that we can derive from the carbon-13 compounds. The idea is to saturate the compound of interest at the beginning and then watch it recover following saturation. For example, as seen in the images here on the right for lactate, where we saturated and then it grows back. And from these time histories, then we can quantitatively calculate the metabolic exchange rates. Now, a different way to go after this problem, as opposed to tailoring the RF pulse flip angles, is to use pulse sequences that are just very efficient in how they use the magnetization. Some examples of these are spin echo train pulse sequences such as RARE, or the balanced steady-state free precession pulse sequences, which are used a lot in conventional proton clinical imaging. These were used a lot in some of the early studies based on angiography and perfusion. Here's a couple of examples from the work of Goldman using hyperpolarized urea, but these can also be used for metabolic imaging. This is an example where you use a multi-echo balanced SSFP image to get images of lactate, pyruvate hydrate, alanine, and pyruvate. Now, the last thing I wanted to show in this category was something that combines two of these concepts. The concept of individual metabolite excitation was one of these efficient sequences, a balanced SSFP. It turns out that when you use very low flip angles for balanced steady-state free precession imaging, you get a very narrow bands of excitation that are equally spaced in frequency. So this is over here on the left. This shows the transverse magnetization versus pulse number, and this is equivalent to this axis here is proportional to frequency. We see we get very distinct excitation at certain frequencies, and here's a cut out of this plot. We see that we excite sharply at these 2 points, and here's our transverse magnetization. So essentially what we can do is take this location where we have this very sharp excitation and then place that at the frequency of one of the metabolites of interest. We can also, as was demonstrated in this article by Manson, you can use a flip angle modulation and actually smooth out this so you don't have these rapidly oscillating side lobes. Here's an example how they applied this to imaging bicarbonate in the pig heart. This is the carbon-13 image, and here's the carbon-13 image overlaid on some proton scout images. Now, for the next part of the talk, and the last part of the talk, I want to talk about some of the strategies that have been used for accelerating the acquisition, both accelerating spatial encoding and accelerating spectral encoding. The general things that have been done are to use time-varying readout gradients, such as an oscillating echo-planar gradient or a spiral gradient, to use optimized spectral sampling, for example, the ideal method, and there's some more general methods, of course, you can use, such as parallel imaging, compressed sensing, which are applicable to a wide variety of things. We'll look at one example that uses compressed sensing. Now, before we get to those, I wanted to make a general comment about accelerating and how that plays into hyperpolarized compounds. Now, if we undersample either in the spatial or spectral domain using a variety of techniques, or if we use more efficient K-space trajectories, the one thing that we're going to do is we're going to do fewer excitations. So if you think about the consequence of this with regard to signal-to-noise behavior, if we do standard steady-state proton imaging, or this is what is most of clinical imaging, the magnetization that's generated, the transverse magnetization, is the same with each excitation pulse. So if you do fewer excitations because you're undersampling for some reason, then you get less noise averaging, which means your signal-to-noise goes down as the square root of the experiment duration. So you lose signal-to-noise when you go faster, and that's what you're very familiar with in standard imaging. However, with these hyperpolarized compounds, if we design the flip angles properly, for example, if we use this variable flip angle series that maintains constant signal depending on the number of pulses, then what we're able to do is increase the transverse magnetization per excitation in proportion to how much we drop the number. And it actually turns out that, aside from factors I'll mention in a second, the signal to noise can be independent of the experiment duration. So you can accelerate the experiment but still maintain signal to noise. Where you can get losses if you're doing parallel imaging, you're still going to have G-factor losses, and of course you always have to deal with T1 decay. But this is a major difference between standard steady-state imaging and what you can do with these hyperpolarized compounds. So let's turn back to accelerating spatial and spectral encoding. The baseline for doing combined spatial and spectral encoding is, of course, standard chemical shift imaging. We know in chemical shift imaging, we use a phase encoding a phase encoding gradient for each spatial direction that we want to encode, and then we simply sample an FID. So the disadvantage of this technique, although it has been applied to a lot of carbon-13 experiments, and it can be very useful, but The disadvantage is phase encoding, as you know, is very slow. You have to step through one gradient strength for each dimension in your matrix. And what you get here may be a spectral bandwidth that's unnecessarily high, that's much higher than you need. What that means is we have some opportunity here to speed things up. One straightforward thing we can do, borrowing from the work in proton MRI, is to use what's called echo-planar spectroscopic imaging. First introduced quite a few years ago by Mansfield, and it's been used a lot for proton spectroscopic imaging. So the idea is we take one of these phase encoding gradients, and instead of sampling after the gradients, we sample with the readout gradient on. That gives us our spatial encoding in place of this gradient. And then we oscillate that gradient and sample over and over again. That gives us our spectral or temporal sampling. So what we've done is multiplex the spatial encoding with the temporal sampling. The price we pay is that we've reduced our spectral bandwidth. It's now 1 over the echo spacing, but in many cases this is still sufficient, and this will let us accelerate by quite a large factor but still get the information we need. Now we can extend this even faster by going to spiral encoding. In this case, we're replacing 2 phase encoding gradients with the spiral encoding along 2 axes. One drawback or one issue that you have to deal with this technique is because the spiral readouts are relatively long compared to, example, that oscillating echo-planar gradient, that we may need to take advantage of sparse spectrums like we have with carbon-13 so that we can undersample in the time domain and then use an optimized reconstruction to pull back the information, even though, for example, we may have aliased resonances. For example, Dirk Meyer and his colleagues have demonstrated this in a 2D form where they're able to get sub-second dynamic imaging of hyperpolarized carbon-13 compounds. This approach has also been demonstrated in the radial mode, a recent article by Ramirez. It's the same basic idea, but using radial readouts, and so they've replaced 2 of the gradients, again, similar to this case with spiral, with a radial readout that goes through different projection angles as it steps down the echo train. Now, in the context of spiral spectroscopic imaging, I noted that you may want to take advantage of the fact that you have a sparse spectrum to be able to undersample it, but still get out the information you need. So the extreme case of this is essentially the technique that was introduced many years ago by Tom Dixon in the context of fat water imaging, where you try to take a very small number of points, but take advantage of the a priori information you have about the spectrum to actually be able to pull out the peaks. This shows us his original idea, which was to just sample data at 2 different echo times, one where the magnetization for water and where opposed, one where they're in phase, and under the ideal conditions, you can add and subtract these images to just get the water and the fat separated. Now, in practice, you have to deal with other factors. One of the main things in human proton imaging is field inhomogeneity. There may be other factors such as T2 star decay. But what was recognized is that you can simply extend this. In fact, a few years after Dixon's work, Gary Glover noted that we could take 3 data points or 3 TEs instead of 2, and that we can account for inhomogeneities. And this was later optimized, again in the context of fat water imaging, by Scott Reeder, who introduced this technique called IDEAL, where it takes a small number of points at different echo times and then use an iterative least squares estimation problem to get out the spectral lines that you're interested in. This is a very powerful technique, and it's been demonstrated for carbon-13 by Wiesinger. Here's an example of their technique. They take an FID acquisition to get the spectral information, and then a small number of single-shot spirals at different echo times. Here's the quality of the results they can get. These are dynamic metabolic images in the heart. Now, the important difference between practically what you can do with this and what you do with the standard spiral chemical shift imaging technique is you need much fewer time points, much fewer echo times. This particular work used 7 echo times, whereas the full spectroscopic CSI has used tens or even tens of points, tens of different time points in order to pull out the data. This has also been demonstrated with echo-planar imaging. I think in these results they also used an echo-planar gradient, but 7 different echo times in the ideal method to decompose the different metabolites in the images. Now, when we were talking about RF pulses and excitation, I mentioned the work of Angus Lau, where they excited one metabolite at a time. This is something that you can use to also do very rapid imaging by simply appending a very rapid acquisition method after you excite one metabolite. And in fact, in that work, what they did was use a single shot spiral after each excitation pulse that just excited one metabolite. So what they were able to do is to get a complete 2D image with each excitation pulse. Now, many of you know about chemical shift artifact from proton imaging, which in the context of clinical imaging is an artifact. It's the displacement of a chemically shifted species along the readout direction compared to another one. Here are some images in the abdomen. We see this is axial down in the lower abdomen. We see the kidneys and the surrounding fat, and we have relatively low receiver bandwidth. We get this artifactual dark line around the kidney shown here at the red arrow because the water appears displaced or shifted compared to the fat. Well, you can actually take advantage of this. Instead of it being an artifact, you can take advantage of it when you have several chemical shifts to speed up the encoding. This is some work from von Moors, where what you do is choose the receiver bandwidth, or equivalently the gradient strength, in combination with the field of view in the spatial resolution, so that you separate the chemical shifts of interest along the frequency encoding direction. And these dashed lines just show what the spatial extent of the object can be. Here on the right, we have an example of doing this in the mouse. This is the frequency encoding direction. It's vertical in this image, and during one readout, we've encoded lactate, alanine, and pyruvate separated along the readout direction. So we get all three of them at the same time, simultaneously. So that it does have constraints with regard to the gradient strengths and the geometry you can use, but it's a very fast way to read out things simultaneously. My last comment, I just want to give an example of compressed sensing. Just a little bit of background, or remember that when we talk about compressed sensing, the image is compressible if it has a sparse representation in some domain. For example, if you can represent it by wavelets and only a few coefficients or a relatively small number of coefficients are used to represent it. If that's the case, then the idea is to do undersampling, but not regular undersampling like we use in parallel imaging, but random undersampling so that the aliasing artifacts are incoherent. Then we can use a nonlinear reconstruction to recover the image. And the important thing about accelerating with compressed sensing is that it's independent of the RF coil geometry. You don't have to have an array coil in order to do it. Or if you do have an array coil, you can combine compressed sensing with parallel imaging. Here's an example of this applied to carbon-13 by Hu and colleagues. This is again the the low flip angle, double spin echo EPSI sequence that we saw. They've added a randomly blipped gradient here along the GX axis, shown here in the inset. And what this does is allow us to sample at random spacings along the spectral domain. And then this pattern is varied as you step through the phase encoding gradient on the other axis. And you get a random sampling pattern that looks like this. So we have the spatial direction here vertically, the spectral dimension left to right, and the black areas are where we didn't sample data. So they've not sampled half the data for this particular example. You use an appropriate nonlinear reconstruction, you can get results as shown here. This compares a fully sampled acquisition in an animal, 8x8, to a compressed sensing acquisition where we've used the acceleration to speed it up and get twice the resolution in one direction. We see that the spectra compare quite favorably with regard to the large peaks, the pyruvate and the lactate, but you do notice the smaller spectral peaks are lost. And this is one of the properties that you have to deal with in compressed sensing, is that when things get close to the noise floor, the reconstruction will suppress them. So in closing, what we've talked about is that the non-equilibrium hyperpolarized magnetization combined with its limited lifetime and the limited amount of agent in the exchange among chemically shifted states leads us to optimize the imaging strategies in order to make the most of our agent and to go as fast as we can. We talked about the management of the non-equilibrium magnetization, which led to optimizing the RF excitation history, particularly using variable flip angles, and also using flip angles that are tailored to the specific metabolites. Considering the limited T1 of the agents and the limited amount of the agents, it's important to accelerate both the spatial and spectral encoding. We went through several ways of doing this. In particular using time-varying gradients, such as echo-planar gradients and spiral, and different undersampling schemes, such as the ideal spectral undersampling or the more general technique of compressed sensing. Thank you.